All right, new topic. So last time we finished up talking about diodes. We're now going to talk about transistors. So we are finally getting to the really important stuff that you're actually going to need to know to build the damn robot, right? This is the exciting part, building towards at the end of the semester. Before we even talk about electricity, I'm going to stick with fluid analogy again. Just kind of the concept of a control valve, right? We are going to think of transistors in this course as electronic control valves for things that require a lot of current, like motors. So this is something you deal with in everyday life, in my little terrible drawing here, just like a faucet, right? The faucet for a hose, okay? That there's some ball valve in there, and you turning that valve controls the amount of flow through the faucet. You know, sink faucet, shower head, hose, whatever, right? You are not pushing the water yourself. This is what I mean by controlling. You are not providing the power to move the water. That is coming from some external pressure source, whether it's a well pump or water tank in a water tower in a city, whatever, right? You are not providing the power. You are just, through the motion of your wrist, turning this little valve, controlling a much larger flow. Okay, so transistors, so this is your control, and you're using that control valve to control this flow. Conceptually, that's what we're doing with transistors. And the transistors in this course that you're going to see are going to be really big, right? We just had the ASML guy here talking about Moore's law, and now we can fit billions or however many transistors on a chip, and this has been getting smaller and smaller and smaller over the years. When you go pick up the MOSFET in lab, it's like almost as big as your thumb, right? So we're not talking about microscopic transistors that are a few atoms thick or whatever they're down to. We're talking about big honking transistors that can handle a lot of power because they need to dissipate a lot of heat. Okay, so when you look at them physically, if you look at the BJT in your kit, which is another type of transistor we're going to talk about today, it's this little thing, kind of a little black plastic package with 3 legs, like that. And that package is called TO92. So TO stands for transistor outline. These things kind of come in different physical packages. When you pick up the MOSFET, it's huge, and it has this big metal tab on the back, because you can actually bolt a heat sink onto it. Again, I had a printout and I forgot to bring it today, but again, a lot of you are taking heat transfer right now. It's this big metal thing with a bunch of fins sticking out to give it more surface area for cooling. Okay, so we're talking about things that are big and need to dissipate a lot of heat, not tiny fitting billions. And so conceptually or electronically, the operation is kind of the same, but we're not talking about squeezing billions of them into an Intel processor in this class. Okay, so again, think of it. This is going to be specifically in the context of controlling stuff with the Arduino, or when we want the Arduino to control some large load, which in our case is going to be motors, but could also be something like really big, really bright LEDs, more like car headlights or something, as opposed to the little tiny ones you've seen in your kit or in lab so far. Okay. The circuit diagram symbol for the type of transistor we're going to talk about now, which is specifically an NPN Bipolar Junction transistor, or BJT for short. And I think I mentioned last time there are a dozen different types of transistor. There's NPN, there's PNP. This all relates to the different arrangements of these different doped semiconductor materials. We're not getting into any of that physics. In this class, we're only talking about NPN BJTs today, so don't worry about the other types, because this is kind of the common type you would use when you need to do something like control a motor with an Arduino, and we're not going to worry about the other types as much. Okay, circuit diagram symbol for that has 3 terminals that look like that. Okay, so we got a circle with a line coming up from the left, and then kind of this weird stuff inside there, a line going out the top and a line going out the bottom. The pin on the left is called the base, abbreviated B. The pin on the top is called the collector, abbreviated C. And the pin on the bottom is called the emitter, abbreviated E. And what we're going to see is that a tiny current into the base, so this is a current control device, I'm not physically turning a valve, I'm controlling it electronically. A really tiny current into the base allows us to control a much larger current into the collector. So we're not drawing the whole circuit diagram yet. We'll show how we connect it to other stuff later, but basically I'm using a tiny or low power control signal here from something like your Arduino, which can't provide enough power to control a motor directly, to control, again, a motor, solenoid, really bright LED, something that requires a lot more current. Okay, so conceptually, that's where we're headed. Okay, so going back to the water analogy, unlike things we've seen so far like a resistor, where it's just a single kind of linear equation for the whole thing, this part is going to have 3 different modes of operation. So I'm going to attempt an artist rendering here of a pipe with kind of a T connection where I have a smaller little pipe coming in from the side here, and there is a little flap attached there that can pivot about that point. So does that representation make sense? I have kind of a rigid flap that is currently blocking both sections of the pipe, but it can pivot like this. And say I have a bunch of water up here from some external pressure source. Okay, that's coming from some extra other tank or something. But I can send water in, I can force water in from the left over here. Okay, so if that flow is 0, if that current is 0, then this flap doesn't open at all, and then this flow is also 0. So this is just off. Okay, this is called the cutoff region. It's not very exciting. And we'll talk about the actual electrical way this works in a minute, but just to kind of using the pipe analogy here, I think this helps visualize how it works. So that's the cutoff, electrical, both currents are 0, nothing exciting happening. As I start pushing water in this way, that flap is going to start rotating open. Okay, so I push enough water in, that flap rotates a little bit. Now I'm letting water flow through from the top. Right, so I'm pushing a little bit of current in there, it's non-zero, and now I can kind of have more flow up from my bigger pressure source. And here I kind of have a linear operation, right? The more water I push in here, the more this flap is going to open, and the more water is going to come down. Okay, so this is called the active region, where I have this kind of linear relationship. More current from the control pin gives me more current through the big pipe. Until eventually, this flap kind of opens all the way and can't open any further. Right, so I get to a point where that flap is now open all the way, and even if I try to keep pumping more current in from the left, that's kind of maxed out the amount of current I can get through the big pipe. I think I can keep trying to pour more water in here, but it doesn't matter because I've already opened this all the way. I'm not going to get any more flow that way. And that is called the saturation region. And again, this is not, don't take this too literally. There's not literally a little door opening in there letting electrons through, right? That's, again, all the kind of physics of the semiconductors, and where sometimes there's a channel that can conduct or a channel that can't conduct depending on voltages and all that stuff. Totally glossing over that in this class. Yes?
So like in this analogy that you're giving, we're seeing some of that the representative IB that actually goes into the mainstream. Is that what's happening with the transistor?
Yes, so I'm going to label that better on kind of the next diagram, but yes, IB also comes out down here. So the emitter current is equal to the base current plus the collector current, but what we'll see in a second, the collector current is usually at least a factor of 100 larger. So the base current is, the emitter current is almost equal to the collector current, kind of within like 1%. But yes, so the flows here are also merging. So base current comes in, collector current comes in, like that. Sorry, that wasn't clear. Okay. Other questions on the conceptual model? Because again, we should now be in like fully and didn't see this in physics territory, as far as I know, for what they taught in 2213. Everybody cool with this? Yes?
So does it mean like we will have like 2 threshold current from the base to determine, oh, I change it from cutoff to active, I change it from active to saturation?
Sorry, can you repeat the very first part of that question?
Oh, I'm saying like, does it like have like 2, I don't know, like threshold current?
Threshold. So the question was, kind of. So we're going to talk next about how the actual electrical model works and how you determine if you're in active or saturation. This is kind of just purely conceptual without doing any of the math yet. Okay, so fluid analogies are fun, but unfortunately we have to learn how it actually works electrically. So, we'll try and keep that on screen for a little bit so I can kind of draw these next to each other. If we look at the cutoff region with the actual BJT symbol, again, there's my base, there's my collector, there's my emitter. What I'm saying in cutoff is that, I do this in different colors, my base current is just 0, and my collector current is pretty much 0. It might actually be some leakage current on the order of nanoamps or picoamps or something, but for purposes of this course, we just round that down to 0, close enough, and then say our emitter current. So basically it's saying we have 0 current everywhere, and the voltage between the base and the emitter, so if I measured those 2 points, is less than about 0.6 or 0.7 volts. So we kind of treat, see this little arrow that I drew in there, not very well? We kind of think of that junction sort of like a diode, where we need to apply enough voltage across it to get it to start conducting and open up the valve. Okay, so if I don't apply enough voltage, and therefore have enough current here, nothing's gonna happen. Again, not very exciting. Okay? In the active region, I'm going to redraw the symbol. Base, collector, emitter. I now have some non-zero current IB into the base. The collector current IC is proportional to the base current. So it's the base current times some constant beta that, depending on the transistor, usually is going to be in the hundreds-ish, dozens or hundreds, not thousands, not millions, but it's amplifying that base current by roughly a factor of 100. Okay, and then the emitter current is then the sum of those 2 currents because they're both flowing down out the emitter. So that's IB plus IC, where again, beta is usually somewhere around 100. And now that BE junction acts kind of like a diode in the forward biased or conducting region, so VBE is kind of about 0.6 volts. Okay? Cool. How do we know if we're in the saturation region? And this part probably won't be fully clear until we walk fully through an example by the end of class today, but we're going to kind of write down the conditions for this first. So again, I have my base, collector, emitter, still have my base current IB, still have my collector current IC, and I still have my emitter current, which is equal to my base current plus my collector current. But now once I'm in the saturation region, my collector current is going to be less than beta times IB. So I'm no longer getting that full linear relationship, and if I were to make a graph of the collector current versus the base current, and this is what you're going to see on homework 5, for a while I would have a linear relationship, right? So this is the active region. And if I were to continue in the active region forever, that line would just keep going up diagonally, right? If I just had that proportional relationship forever, but in reality what you see is that eventually it sort of levels off and saturates. So this is saying IC is less than beta IB, that's saying this part of the line is less than what it would be if I was continuing that linear relationship, right? And that's here, again, if you imagine like what would happen if I just kept pushing more water in and this just kept increasing, well then I would keep going up linearly, but here at some point it saturates instead. Okay? And when this happens, the voltage between the collector and the emitter, which we haven't really talked about yet, is going to be equal to something called the saturation voltage, which is usually about 0.2 volts, so a little lower. And we're going to talk, that part isn't as clear until we actually go through the example later. and the voltage between the base and the emitter is still forward biased or still conducting, so that's still about 0.6 volts. Okay, so these are kind of our three regions of operation. I should have labeled this one saturation, and then kind of way down there, if we were to zoom in on the bottom left corner of the graph, we have cutoff, where we're just not doing anything. Yes?
Was 0.6 and 0.2 like an arbitrary values each you chose? Or?
No, these are kind of based on the semiconductor physics. For again, for a typical diode, this value is around 0.6 or 0.7, and then again the physics are a little different for this junction, but the volt that's typically slightly lower. So those are kind of typical representative values, but for a specific transistor, you would look in the data sheet, and kind of it may vary depending on the materials that transistor is made of. Okay. Yes?
Do you mind moving the page slightly up?
So I'm moving this one up?
Yeah.
Okay, sorry, I was trying to keep the, let's just abandon this page for now. Hope everybody had that part written down. Is that better? Okay. And a note on this graph, sometimes what you will see if you look in a textbook is a graph that looks very similar but actually has different axis labels. So it'll have the collector current on the y-axis and VCE on the x-axis, so the voltage between the collector and the emitter. And there will be a bunch of curves that look like this for increasing values of IB. So each one of those curves represents a different base current. And this is a little confusing because on this graph, the active region is the flat part, right? So as I increase my value of IB, I move up to a higher value of IC. And the saturation region is over here, and kind of the diagonal part where I say, okay, my actual current that I'm getting is less than what I would get for a linear relationship with IB. I don't like this version of the graph because I think it's kind of more confusing to think about, well, what is VCE, right? We're talking about controlling or pushing in more base current. How do I control this voltage? So I prefer this version of the graph, but if you go look at a textbook or the Wikipedia page about BJTs, you will see this version, and you have to be careful because again, the shape looks the same, but the axis labels are different. So in this class and on the homework, we're going to use this version that may make a bunch of electrical engineers mad. I don't know, but I think this one's more intuitive, especially when talking about the water analogy. Okay. So where we're going with the rest of class today is, okay, it's kind of, if we're thinking about this as controlling something with an Arduino, right? We connect it to an Arduino pin, and if the Arduino pin is just off, then okay, the transistor's off. Great. And the other types of transistors we're not talking about, so there are kinds where you can reverse this, and kind of the transistor turns on when the input has no current, and then the transistor turns off. So kind of like a reverse light switch or something. So we're not worrying about that kind. We're just thinking about this kind where if the input is off, the output is off. If the input is on, then the output is on, but we don't necessarily know whether we're in the active or saturation region if we're on unless we do some math. So that's what we're going to do with the rest of the time today. So conceptual operation questions before we kind of get more into the math part. Okay. So we are going to try and cram the first part of this example onto this page and then see, probably have to go up to another page. So, example problem. So we have V in, which is our signal that we're going to send into the circuit. And now we're actually going to look at, like I've only been drawing this symbol so far, what happens when you actually connect it to other stuff. Right? For a BJT, we're going to have a base resistor, RB. I'll explain more about that in a second after I draw the whole circuit. And then I'm going to have our BJT. We're going to have our load resistor, RL. So this is whatever load we're controlling that requires more power than whatever VN is coming from. So if VN is coming from an Arduino, we're going to have that connected to a positive power supply with yet another subscript that we haven't seen yet. Depending on where you look, the subscripts for these are always different. You might see VCC a lot for the positive power supply. Okay, and then we're just going to have the emitter connected to ground. Okay, so if you think about how currents are flowing when this is on, we're going to have the base current into the base. The collector current goes through the load resistor, and then the emitter current is still going to be the base current plus the collector current. Okay, now why do we need a base resistor? Why don't I just connect the voltage directly to the base of the transistor? For the same reason we talked about needing a current limiting resistor for LEDs, right? If this junction acts sort of like a diode that only has a forward voltage drop of 0.6, 0.7 volts, and I just apply 5 volts directly to the base, then I'm going to blow up my transistor. Okay, so this base resistor acts just like the current limiting resistor on an LED that we saw last time. Okay, it helps limit, there is a voltage drop over this resistor, and it helps limit the current into the base to avoid blowing up the transistor. Okay, that's not going to be the case with MOSFETs, which we'll talk about next time. Yes, in the back.
What is the label according to RL? Does that say band resistor?
Load resistor over here, sorry. Base resistor and load resistor. I can link. Okay. We're going to have a base resistor value of 1 kilo ohm, a load resistor value of 30 ohms. VCC, our external power supply, is going to be 12 volts. And for this transistor, we're going to say we have a saturation voltage of 0.2 volts, and beta is 100. Okay? So, what's going to happen if, say, our input voltage Vn is only a half a volt? Well, we have to redraw this circuit 3 times, so bear with me. If our input voltage is only half a volt, then it's not high enough to forward bias the base, just like we have with LEDs, right? I know if I need kind of a minimum voltage drop of 0.6 volts there, and I only do 0.5 volts here, it's not high enough, so just everything is zero here. Boring. Base current is 0, collector current is 0, it's just off. Okay? So what we're going to do now is look at what happens if we keep increasing this voltage. And then we'll do a poll everywhere in a minute once I set up the next part to wake everybody up a bit. So, I'm trying to slide this up as far as I can and keep that part. Okay, what happens if we increase that voltage to 3.3 volts? Which is kind of a common logic level you can encounter on some Arduino models. Okay, my load resistor, VCC, RL, ground. So if I assume I'm in the active region now, and my base, at my emitter, at my collector, I have all they scrolled off screen here, but hopefully you wrote down all the parameters previously. So, actually I'll jot some of them down here. I have a 1 kilo ohm resistor there, I have VCC equals 12 volts, and I have RL equals 30 ohms. And if I assume I'm in the active region, then I know VBE, so the voltage between there and there, is 0.6 volts. And I want to know what is my current through the load, okay, through the load resistor, which is the same as the collector current. What is IC? Okay? I'm going to activate that as a poll. Think about how you can figure that out. Okay? I know that the voltage here is 0 because this is connected to ground, right? And I'm telling you that if I'm in the active region, the voltage drop from here to here is about 0.6 volts. So I know the voltage at B. Okay? I know and as we've seen a dozen times at this point, I know the voltage drop over this resistor. If I can calculate the current through that resistor. So that is all the same as stuff you've done previously in the class. The new thing we have now that we have a transistor is we have a relationship between this current and that current, right? I'm not going to draw it again. Look back from your notes from 10 minutes ago. I now have an equation where if I can find this current, I should be able to find that current. Okay? So if I know my input voltage, I choose a load resistor, and I know the gain of the transistor, then I should be able to, and I know the resistance of my load, then I should be able to calculate the current through the load. Yes. Is that a stretch or a question? No? Okay.
Well, so no. This thing supplies not that much, and that thing supplies way more. Because he was talking earlier about how this thing is just like the switch, and that is the actual power. So it's on.
What is that?
I guess I need to figure out this why we did you said the whole thing. Then you're having a drop from 3.3 to 0.6 across the wires.
I see it.
Oh, yeah. Unless you have it.
Okay, let's give it another 30 seconds for around 100 responses. 20. Ten. 5. 4, 3, 2, 1. Deactivate. Okay. Let's see. Most of you, okay, about half of you got the correct answer, which was D, 270 milliamps. So, let's work through how we do this. Okay, step 1. Okay, identify the voltage at the base. And we know that voltage here at the emitter is 0 volts, because that's connected to ground, right? We know that this thing acts like a forward bias diode, so the voltage at the base is 0.6 volts. Okay, step 1. Step 2. I know the voltage drop over the base resistor, so I can find the current through the base resistor. Okay? As always, our good friend Ohm's law, V equals IR, voltage drop across that resistor is 3.3 volts minus 0.6 volts. That's going to equal the base current times the value of that base resistor, which is 1 kilo. Okay, solve that for the base current, and I get IB equals 2.7 milliamps. Okay, I didn't ask you for the base current, I asked you for the collector current. And I know that in the active region for a BJT, this is what we wrote down back here, the collector current is just equal to beta times the base current. Right, so the collector current, IC, equals 100 times 2.7 milliamps, which is 270 milliamps. Okay? Questions on how I got 270 milliamps for the collector current? Okay, just find the current through the base resistor, multiply it by beta to get the current through the load resistor. No other, you don't need to, in this case, I didn't need to find the collector voltage or the voltage drop across this resistor. I just had that equation, collector current equals beta times base current. Okay, so don't be shy. Anybody who didn't get that initially have question or confusion about how that calculation worked? In the back, thank you.
The 3.3 minus the 0.6?
Yes.
What do those represent? Like that's
That is the voltage drop across this resistor. So I was lazy and didn't write out units in that equation, right? But my input voltage is 3.3. I know the voltage here is 0.6, so the voltage drop across this resistor is 3.3 minus 0.6. Believe me? Is it just too small, or?
So BE is 0,
Yes.
and then
And then this, the BE junction, think of it, remember, think of it like a diode, where we have the IB curve that looks, in the ideal case, like this, where it's just flat, and then a straight line. So think of it like a diode, where that straight line happens at 0.6, so it just has a constant voltage drop across it. Okay, so don't think of BE like a resistor, just think of it like a diode. So if the emitter is tied to ground, so that's 0 volts, then and we're conducting, then it has to be 0.6 there. That was not the case when we were in cutoff, right? So I actually shouldn't have drawn that here. This is only true if we're forward biased and conducting. So in this case, if we have 0 current through the base resistor, then the voltage there is actually going to be 0.5 again, right? Because I have no, as we've seen, sometimes I have no current through that resistor. I have no voltage drop across this resistor, so if the voltage there is 0.5, the voltage there must also be 0.5, so I should cross that out. In this case, I do have current through this resistor because this voltage is higher than 0.6, so I'm going to have some current, right? But I don't know how much current until I do that calculation and assume I'm going to treat this like a diode, the voltage there is 0.6. Good? Okay. Okay. What happens if we then, I went too far. What happens if we keep dialing up that voltage? Okay, now I'm going to hook it up to 5 volts. So the Arduinos in your kits are, there are 3.3 volt Arduinos out there, but the ones in your kits are 5 volt. So bear with me as I redraw the whole thing again. So now we're going to send 5 volts in. So we'll have our load resistor, VCC, RL, emitter to ground. Okay, let me see how I have this next question worded. So, if you assume the transistor is in the active region, okay, that's important. If you assume active region, what is the voltage at C? Okay, so I'm asking you for an extra step now. I'm not just asking you to find the collector current. I'm asking you to find the voltage at C if you assume it's in the active region. Which is the same thing as since VE is 0, saying VCE is the same thing as asking what's the voltage at C. Okay, so you can start off with the same assumption as last time. Okay, so start off assuming this voltage is high enough that this is forward biased or forward conducting, so the voltage there is 0.6 volts again. And I still have 1 kilo ohm there. So then there's an extra step now. I can calculate this current, I can calculate that current, but then I need to calculate this voltage. Okay, and the only new thing here is the transistor, the relationship between this current and that current. The calculating currents and voltage drops across resistors is still just all Ohm's law. Okay, if I assume it's in the active region, what is that voltage? Yes?
12.9 volts.
Oh, it's a pole everywhere, don't say it out loud. It's fine. Although I will tell you that was wrong. So that was actually not one of the pole everywhere options. But, yes. Yeah, VCC is still 12 volts. Sorry, I just haven't been rewriting that each time. VCC, all the previous, VCC is still 12, RL is still 30 ohms, I just didn't rewrite it. Answers are trickling in a little slower this time. Let's give like another minute. We're at about 90 replies. Okay, let's do 20 seconds. Keep going. Ten, 5, 4, 3, 2, 1. Deactivate. Okay, the correct answer for this question, which doesn't actually make sense, is A, negative 1.2 volts. Right? So if you got that and thought like, wait a minute, that's impossible, it's got to be something else, you're right, that's because it's not in the active region, it's in the saturation region. Okay, so if, work through the calculation, I do the same thing I did last time. Say, okay, I want to find the base current, IB, this voltage is a little higher now, right? So the voltage drop across that resistor is 5 volts, minus 0.6 volts, that's going to equal the base current times the 1 kilo ohm base resistance. That gives me a higher base current than I had last time. I get 4.4 milliamps for the base current, whereas last time I only had 2.7 milliamps. Okay, fine, that's gonna give me, if I assume active region, IC equals 100 times 4.4 milliamps. Okay, now I have a bigger current through the load. I have 440 milliamps, which if I stop there would just seem fine, right? Okay, whatever, I have 440 milliamps through the load. But what we didn't do last time is double check, well, wait a minute, what's the voltage at C? Is that physically possible? And we can find the voltage at C by finding the voltage, just applying Ohm's law to the load resistor, right? So VCC, the power supply voltage, minus VCE, the voltage between here and here, that's the voltage drop across that resistor. This is just 0, equals collector current times the load resistance, 30 ohms, right? So if I solve, I know this is 12 volts, I don't know VCE, equals 0.44 amps times 30 ohms. Solve that for VCE and I get negative 1.2 volts, which doesn't make any sense, right? I can't, and then if I look at this circuit, if I have 12 volts there and ground there, I can't have negative 1.2 volts there. Okay, the collector isn't like that would mean I would also have current flowing in this direction because 0 is higher than negative 1.2. It's not acting like a point sink. I don't have current just disappearing into that point. Is that a question?
So does the voltage, I guess in this case it's negative, but if it was positive, does it travel through the same path as the other current? Or it's just the diagram? It's like
So
or it travels through another path?
No, well, you mean in terms of like where is it physically going in this, inside the device?
I was just curious if it was the same.
We're treating it kind of like treating the transistor like a black box where the collector current comes in here, base current comes in here, and then the sum of those two goes out there. You would have to look at again, you can go on Wikipedia and look at the cross-sectional diagram of what the actual different semiconductor layers are. And again, not taking the fluid analogy too literally, there can be channels or segments of material that switch from not conducting to conducting. So it's kind of like a channel opens up where now electrons and holes can move through. To be honest, I could not teach that without looking it up. Like I would need to go look up the diagram. But again, you can literally go take an entire course on semiconductor physics here, if that's something that interests you. But if you just kind of want the quick overview of what the kind of cross-section of this device looks like and where the channel is actually flowing, you can go look at either in an electronics textbook or Wikipedia will kind of have diagrams of all the different transistors and what's actually going on inside. We just don't have time to get into it this class. Okay. Going back to this. So if I assumed I was in the active region, that's kind of like saying, okay, remember we have this graph of the collector current versus the base current, and I know it's linear for a while, and eventually it saturates. I kind of assumed I was still out here, right? Which isn't true because I've hit saturation. So if I assume I'm out here, then I find a current for this resistor that is too big, and then the voltage drop that I would calculate is so big that it just doesn't make any sense. So I know I have to be in the saturation region. And in the saturation region, we'll write this in a different color, we assume that here we've kind of reached that saturation voltage. So if you think of this as this current keeps getting bigger and bigger, the voltage drop over this resistor keeps getting bigger, and this voltage keeps getting closer and closer to 0, right? So think, when I start out, if I have no current, I have 12 volts here, then I'm also going to have 12 volts here if there's no current through this resistor. As I keep dialing that current up by increasing the base current, this is going to go 11 volts, 10 volts, 9, 8, 7, 6, 5, 4, all the way down until it hits kind of the floor or the minimum is that about 0.2 volts. Okay, so it can't go, not only can it not go negative, it can't actually get all the way down to 0. It kind of, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.2, and it kind of maxes out there. And that's where we hit this inflection point on the graph where now we're saturated and the current's no longer increasing linearly. Okay, so one last poll everywhere with the remaining time. If I assume I'm in saturation, so now forget previously we were assuming collector current was proportional to the base current. We know we're not in the active region, so that can't be true. Now the collector current is going to be less than beta times the base current, but now I know this is true. Now I know the voltage at C. So in that case, what is the actual, sorry, I skipped a hole there by accident. What is the collector current if you assume the transition is in, sorry. If you assume it's in the saturation region, then what is the collector current? Okay, so this equation no longer applies because I know I'm not in the active region, but I know this voltage now. So now what is the collector current?
I guess he just chose us.
Okay, this one should be a pretty straightforward Ohm's law because again, now you're not even worried about this extra transistor relationship. You know VCC, you know we've reached saturation, so we know VC, so you know the voltage drop over this resistor, so that should just be a really straightforward current calculation. You don't even have to worry about the base current. I mean, we had already calculated it anyway, but you don't have to worry about it. Okay, I'll do that just like another 15 seconds so I have time to go through the solution. 10, 5, 4, 3, 2, 1, deactivates. Correct answer is 393 milliamps, which about 2/3 of you got. So, again, I can assume, now I know the voltage drop over this resistor, right? I know that is 12 volts. If I assume I have VSAT here, then I know that is 0.2 volts on this end. So I know the voltage drop over that resistor is just 12 volts minus 0.2 volts. That's going to equal the current through that resistor times that resistor, RL. So if I solve that, unless I screwed up, I get the collector current equals 393 milliamps, which is less than what we would have calculated before if we assumed we were still on linear, right? So here we got 440 milliamps when we were assumed we were in the active region. So that's like assuming the linear relationship applied and we were still up there somewhere. So this isn't scale at all, but we're actually in saturation down here. So that's the difference between this 440 and this 393. Okay, so you don't kind of just get a free increase forever. Eventually the physics of the device can limit you to how much current you can get through the load. Unless, of course, you could increase your supply voltage, right? So if I said, okay, I actually need 500 milliamps through this load or something, then I would need to apply a bigger supply voltage here, and then I could get more current through this resistor before I eventually still hit that saturation voltage down here. Okay, we've got 0 minutes left, so if you have questions, as usual, I'll be here after class. Thank you.